So let's proceed and let's turn this two-dimensional wave equation that we now know in a continuous form into something we can solve on the computer. So we try to apply our finite difference approximation to this equation in 2 dimensions. So look again at the original equation. First, we have to transform our fields from the continuous world in the discrete world. And we proceed as we did in the one-dimensional case and turn, for example, p as a function of x, z, and t now into its discrete version, which again we use upper index n for time. And now we have 2 lower indices, j and k, that denote the space dependence. And the same applies to the other fields, like the velocity field. This is only space dependent, so c as a function of x and z turns into c of jk. And similar also the source term that depends both on space jk and on time n. Now with this discrete version, of course, we have now the space discretized in j dx and k dz, but now it's a very important point. This doesn't make it more simple, but for simplicity, we assume that dz is equal to dx. So basically we have the same space increment in x and z. And that makes later an analytical treatment easier. And also we have the discrete time. Our time step is dt, so time is discretized as n times dt. Before proceeding to the finite difference approximation, let's look again how this discretization looks like graphically. So basically we now have a discrete version of space, which is in this case a regular grid in 2 dimensions, here shown horizontally as the 2 axes x, z, so j and k, and the vertical axis is time. So basically what we will do is we have to find a scheme that extrapolates the space-dependent fields, like the pressure field, into the next time levels as we did in the one-dimensional case. And now we proceed and replace the partial derivatives by their finite difference approximations. So let's first write down the wave equation again in its discrete version, and we have the partial derivatives on both sides of the equal sign. Let's start with a time derivative. That's actually straightforward. It's exactly the same procedure as was the case in one dimension. So we replace the second time derivative by the approximation for the second derivative. So for that, we need, of course, the time levels p of n minus 1, p of n, and p of n plus 1, and we divide by dt squared. That allows us to calculate the second derivative in time. On the right-hand side now, we have the Laplace operator. And in this case, in the 2-dimensional case, we have the second derivative with respect to the first spatial variable, that's x, and the second space variable, which is z. So they can be treated separately. And just for one example, it's we basically use again the same approximation for the second derivative. For example, p all at time steps n, and we take the difference of p at j plus 1 minus 2p j and p j minus 1. And the k's remain the same. And equivalently also for the z derivative. So basically now we have on both sides the partial derivatives replaced by their finite difference approximations. All the other terms remain the same. And we can now proceed as was the case in the one-dimensional case, to basically put everything that is not the field in the future at n+1 to the right-hand side. So that leads to our well-known extrapolation scheme. Basically, on the left-hand side, we only have the future value of the pressure field at jk, so the index is jk, at time level n+1. That's basically our future time level. And everything on the right-hand side is a function of either the present, which is time step n, or the past, time step n-1. Basically, that's, again, an explicit finite difference extrapolation scheme with which we can now basically loop over all points at one time level, the future time level, and extrapolate the pressure field to obtain progressively the whole system in the space-time. And we're now going to actually look at the Python implementation of this very simple algorithm that's already very powerful. You can actually learn quite a lot of wave phenomena with this very simple scalar acoustic wave equation. And we'll see with the Python code how the solution looks like in 2 dimensions.